guys had something that kind of looked like this on your first one. Okay, so I call it the S sort of thing going on. So when it says, what's that?
I just remembered it.
Are you okay?
Yeah.
That when on the previous slide, when it talks about the three parts of three different chemistries of the reaction, this would be before. You guys buy that? Before EP. This would be at EP, and this would be after EP. Okay. Okay. All right. So we're going to go ahead and basically run through the titration very similar to what y'all did. So in the burette, we're going to put the base this time. That's kind of typical. And then in the receiving flask, we're going to have an aliquot, 25 mils. You guys did 10 mils yesterday, didn't you? 25 mil aliquot of a known molarity of HCl. We know the molarity of the NaOH. And we're going to actually calculate the pH at 3 different places, before, during, and after the equivalence point. Okay. So one of the things, in order to, you're going to, when you do these problems, and again, I'm hoping to get to the assignment slide, but when you do these problems, you're going to want to kind of know which part of the titration you're in. So I'm going to go ahead and write underneath our equation up here. So we said we're going to have 25.00 milliliters of this, the known molarity, okay, and this is what's in this is the titrant, and so we're dripping this in. So the molarity is also known, coincidentally, 0.100 molar. Volume, I'm going to put various because that's what you're dripping in. And actually, various because we're going to look at 20 mils of titrant, 25 mils of titrant, and 30 mils of titrant. Now, do you buy this that the stoichiometry is a 1-to-1, okay, with regard to the acid and the base? Well, does this make sense that the neutralization point, just since they are both 0.1 molar, does this make sense that the neutralization point will be the same volume? So the neutralization point, the equivalence point, actually is 25.00 milliliters in this case. So that's why I mentioned that, because actually this one is at EP, okay? So if 25 mils is at EP, guess what? The first one is before EP, and so actually, and then after EP for number 3. On hints for your homework, I think it's nice that you find that volume of titrant that is your equivalence point, because then you know what chemistry you're after, kind of those 3 sectors. Okay, so let's go with the 20 mils. So in this case, 20 mils of titrant has been added. So if we were going to kind of write under what the situation is here, again we have our 25.00 mils of HCl, known molarity, 0.100 molar. We have 20.00 milliliters of NaOH, also 0.100 molar. This is where I said we're going to kind of count beans, okay? So does this make sense, just eyeballing it, that at this point we have excess HCl. We have excess HCl because this we're still going, okay? All right. So the pH actually is going to be driven by this excess HCl. So we need to count beans and kind of come up with what is the excess HCl. So in order to do that, we're going to come up with what is the millimoles of HCl that were present in that 25 milliliter aliquot. And we're going to go with millimoles because it's easier. So it was 25.00 milliliters. The molarity was 0.100 moles per liter, or 0.100 millimoles per milliliter. So that gives us 2.50, 3 sig figs, 2.50 cute little millimoles of HCl. Okay, so that's what we're dripping into. Now, at this point in the titration, how much NaOH have we added? Well, at this point in the titration, we're at 20 mils. So now we turn our attention, this is the sodium hydroxide, 20.0 milliliters times its molarity, again, 0.100 millimoles per milliliter. So we have dripped in 2.00 millimoles of NaOH. So you got 2.50 millimoles of HCl, 2.00 millimoles of NaOH. That right away should tell you I'm not, and they react in a one-to-one basis. So yeah, I'm under my equivalence point. So we can do another calculation, just a kind of quick and dirty. This is a boring one because the stoichiometry is one-to-one. But we can use the millimoles of NaOH added, the stoichiometry of the balanced equation, 1 millimole of HCl reacts with 1 millimole of NaOH, to get 2.00 millimoles of HCl has been converted to product, which of course product is just salt, NaCl, and H2O. So we're almost there. So that's how much is reacted. Now how much is left? We do a quick subtraction problem. So we started with 2.50 in our 25 milliliter aliquot. We've used up 2.00 because of the NaOH we've added. So that we're left with a whopping 0.500 millimoles of HCl running around before the equivalence point, at that point in the titration. So it's that HCl that is driving the pH. So now we just need to wrestle with those millimoles of HCl to come up with the hydrogen ion concentration. Now HCl is one of the 6 strong acids you need to know. Okay, so since it's a strong acid, it's going to ionize entirely. So the molarity of the HCl will be those 0.50 millimoles divided by the milliliters at this time. Now I wished I would have added to this slide because this 45 milliliters, this is an important point. This is kind of what a fun point. Do you buy this, that this is actually the 25.00 milliliters of HCl plus the 20 milliliters of NaOH. So that's like a moving target, right, as we drip in NaOH. So at this point in the titration, it's 45. All right. So the molarity of the HCl we can get in rounded to 2 significant figures. It looks like 0.011 molar HCl. And here's where, if we want the hydrogen ion concentration, if we recognize HCl as a strong acid, then we know that the hydrogen ion, the molar concentration of the hydrogen ion is equal to the molar concentration of the HCl. And we're almost there. Because the goal at these 3 points is going to knock out a pH. So if we have the hydrogen ion concentration, we can take negative log of that molar concentration and get pH. Looks like this. Rounded to 3. Oh, see? I'm just not sure I'm always consistent. I think, oh no, I was right. 2. Rounded to 2 significant figures. I'm good with that. Okay. All right, that's it. So the next one is kind of, I don't have calculations to follow it up. And it was like what I said a minute ago, where I put the 25 mils and the 0.1 molar here, and the 25 mils and the 0.1 molar there, and the fact that they react in a one-to-one, you know that at 25 mils you are at the equivalence point. At that point, basically, that's all gone and that's all gone. So honestly, that's why this slide says there's nothing over here to monkey with the pH. It's entirely neutral if it's a strong acid and a strong base. Not so with at the equivalence point of the next problem we're going to work. So this is neutral, like Switzerland. Okay, on to, so that's the second one, pH is 7.00. The third one is after the equivalence point. So at 30 mils, I'll go ahead and kind of write under here at the top. At 30 mils, again under HCl, we had a 25.00 milliliter aliquot of 0.100 molar. Here we're at 30 mils of NaOH, again at the same molarity. Okay, so of course this is all gone. Does that make sense? That's all gone. And this is in excess. So this actually is what is driving the pH. That is what's driving the pH. So we need to count extra hydroxides, basically. So here we go. At that point in the titration, the millimoles of NaOH, we can use the milliliters, 30.0 milliliters, times its molarity, 0.100 millimoles of NaOH per milliliter of NaOH, to get 3.00 millimoles of NaOH, which clearly is more than 2.50 millimoles of HCl we started with. So to get the millimoles of NaOH reacted, we can use the millimoles of HCl as a limited reactant. So we put 2.50 millimoles of HCl, use the stoichiometry in the balanced equation, 1 millimole of NaOH will react with 1 millimole of HCl. And so that means that the amount of NaOH that's reacted with that HCl is 2.50 millimoles of NaOH. It's almost intuitive. And honestly, if you want to, as long as you know what you're doing, I don't know if I'm going to say this, but you probably don't need to show all of these steps if you can just kind of say. But be careful because the stoichiometry isn't always one-to-one. So, yeah. I think, Marie, you're right. I don't think I'd skip anything. So these are millimoles of NaOH that's been consumed. So now we need a subtraction. The millimoles that was dripped in, 3.00, minus the millimoles that's been reacted, 2.50. So the difference is kind of symmetric to our first one that we came up with. 0.50 millimoles now of OH, or NaOH. And you kind of heard me say OH minus or hydroxide, because since NaOH is a strong base, here in a minute we're going to assume that every millimole of NaOH gives us 1 millimole of hydroxide ion. Okay, so now we need to ultimately divide those millimoles by the volume. I call it kind of the juicing volume. Oops, did you have a question? No, okay. So the volume at that point in the titration must be what, the 25 milliliters plus the 30 milliliters? So we're at 55 milliliters. Okay, so do you guys see where that came from? Okay. So the molarity of the NaOH is 0.50 millimoles of NaOH divided by the total volume at that point in the titration, 55.0 milliliters of solution. Rounded to two significant figures, that means the molarity of our NaOH is 0.00. See, now that's too many sig figs. I think, yeah. I think it should be 0.0091 molar. I do. Okay. So we still need pH out of this, and you guys did some problems at the beginning of part 4. How do you get pH from the hydroxide ion concentration? So since sodium hydroxide is a strong base, the molar concentration of the hydroxide ion is equal to the molar concentration of the sodium hydroxide salt, which is equal to, again, 0.0091. Cool. Okay, so you could do this a couple different ways. Can't remember what I do. Okay, so I'm going to go with POH and then get the pH from that. So applying the P function to the molar concentration of the hydroxide ion, taking the negative log of 0.0091, rounded to two significant figures, calculator, you get 2.04. Remember, significant figures after applying a log function is reflected in the number of decimal places. So we're almost done. So you can get pH by recognizing that the POH plus the pH is equal to 14.00. So pH then is equal to 14.00 minus the POH, which is 2.04. Rounded to 2 decimals, I get 11.96 as the pH. Seems reasonable. So those would be, for those titration volumes, like, you know, along the x-axis your titration volume, those would be the pHs at those 3 different volumes. Kind of tedious. Okay. So, yeah. So let's take a look. Oh, before we take a look, I guess, on Monday we'll talk more about indicators. But you guys, well, we used an indicator in Chem 1. Phenolphthalein is an indicator. And phenolphthalein works pretty good because right here, you see phenolphthalein? Okay, this is kind of the region where it goes from clear to pink. Okay, so it's not too far. That transition point right there is not too far from there. Okay, so these other ones would work pretty good too. Okay, this was your second titration. And again, we're mixing up a little bit. Instead of a 10 ml aliquot, we're going with 25 milliliter aliquot. We do know the molarity of your the weak acid, acetic acid, CH3COOH. The molarity is 0.100 molar, which kind of makes life easy. We stuck with the same titrant in your burette, sodium hydroxide, again 0.100 molar. So let's see what this looks like. Okay. So this is, and I've got some problems to kind of talk you through this, but I really would suggest that you identify the equivalence point and then proceed from there. So like in Chem 1, I usually put the volume and the molarity and the volume and the molarity. Okay. So since they're also react in a one-to-one stoichiometry, does this make sense that when your equivalence point volume is 25.00 milliliters? It just works out that way. It makes our life easy, but that won't always be the case. And I'll kind of remind you how we go about getting that equivalence point volume. So we're going to do 3 again, and the volumes sound familiar. Okay, we're going to do before EP, that's the 20 mils. We're going to do at EP, that's the 25 mils, and we're going to do after EP. And I'm going to tell you that the chemistry is a little different in each one of these cases. So we need to find what's driving the hydrogen ion concentration to come up with the pH, or the hydroxide ion concentration. Okay, so before the equivalence point, basically, I'm going to kind of go up here. Basically, you have some of your weak acid. I'll put WA for weak acid, strong base. You have some of your weak acid. Some is converted to this. And this is the conjugate base of your weak acid. Do you recognize the CH3COO minus? Okay. So that is your conjugate base of your weak acid. So if we're before the equivalence point, then, and this is kind of, we said one way to make a buffered solution was to take a weak acid like this, react, use a strong base to convert part of it to its conjugate base. That's exactly what we're doing here. So you're ending up with a buffered solution. And let me emphasize, anytime you know you have a buffered solution, you are going to use the Henderson-Hasselbalch equation. Right up here. So for a buffered solution, the pH of the buffered solution is equal to the pKa plus log base 10 of the relative amounts of base, molar concentration or moles, to acid. And these are the conjugate acid-base pairs. So that's the chemistry you have going on when you're reacting a weak acid like acetic acid with a strong base, and you're before the equivalence point. So here we go. Let's count some beans. So before any titrant is added, the millimoles of acetic acid, we can use volume and molarity. Millimoles of acetic acid, we had 25.00 milliliter aliquot times 0.100 millimoles of acetic acid. You can abbreviate it AA if you want. Acetic acid per milliliter of solution. that gave us an adorable 2.50 millimoles of AA, acetic acid. At this point in the titration, this probably seems familiar, we're counting beans. At this point in the titration, we could come up with millimoles of NaOH that we've dripped in. So the millimoles of NaOH is 20.0 millimoles. Its molarity also is 0.100 millimoles of NaOH per milliliter of solution. So that means that we have dripped in 2.00 millimoles of NaOH. Now you need to recognize, like I said, that every millimole of NaOH, since you're before the equivalence point, is going to go ahead and react with your weak acid to form the conjugate, the acetate ion. Okay? So with that in mind, millimoles of acetic acid that reacted, we'll use the limited reactant, 2.00 millimoles of NaOH. Then we use the stoichiometry, 1 millimole of acetic acid over 1 millimole of NaOH from the balanced equation. That means that 2.00 millimoles of acetic acid has reacted. So you know what we're going to do with that, right? Well, we're going to do two things with that, I guess. So we can subtract that from what we started with, okay, to get the millimoles of acetic acid remaining. How many millimoles of acetic acid was left? 2.50 minus 2.00 is 0.50. So actually, if I go with moles of base to moles of acid. Okay, now in this buffered solution, does this make sense? That our acid is our CH3COOH. So we already know that's 0.50 millimoles. Does that make sense? That's our acid. So how much acetate ion was formed? Well, we can do that a couple different ways. I can't remember which way I do it. So we can get the millimoles of the acetate that was formed, the conjugate base, by going back again to the limited reactant, 2.00 millimoles of NaOH, and going back to the balanced chemical equation and recognizing that 1 millimole of acetate, CH3COO, 1 millimole of CH3COO minus was formed for every 1 millimole of NaOH reacted. That's just the boring stoichiometry of this particular reaction. So here we go. 2 millimoles, 2.00 millimoles of CH3COO minus was formed. That's it. But we're close. I think in my notes, I kind of count on the fact that within this unit, we have already wrestled with what is the Ka, maybe we don't. No, I think I do. So we need the Ka of the weak acid. So we need the Ka of CH3COOH. And to plug in there. So we're close. We're after what is the pH at this point in the titration. Yeah, that's what I thought. I kind of, not really great. But hopefully you look back in your notes, okay, is equal to some number, and you go and you get that number and you apply the log function. And you'll find that the pKa for acetic acid is 4.74. You just have to take my word for it. I didn't do it. Redo it. Okay? So rounded to two significant figures, the pH at this point in the titration is 5.34. Phew. Because it's, 5.34. Because you take 4.74 times the log of this ratio, which since it's greater than 1 is going to be positive. And that's it. Okay, that's one of three. So, hopefully, and there aren't a lot of obvious, well, there are patterns in chemistry problems, but this is a pattern in chemistry problem. If you have a weak acid like this, you're titrating with a strong base, before the equivalence point, it's going to be buffered solution, HH equation. At the equivalence point, it's going to be something else. So at the equivalence point, if you want to put ice table, you can, and I'll show you why that is. You are going to use an ice table. Ice, baby. Okay, so at the equivalence point, what happens is all of this is gone, all of your acetic acid is gone, all of your NaOH is gone, totally gone. So the chemistry of your solution is actually being driven by this little guy right here, by your CHO. Okay, CH3COO minus, your acetate ion. And we said that that is what, the conjugate base of a weak acid. Okay, so it's going to be slightly basic. And in order to, once we get the molarity of this, the acetate ion, we're going to get to the pH using an ice table. That's it. So it's basic, pH is greater than 7, driven by the formation of the conjugate base. So here we go. So we need to get to the molarity of the acetate ion at the equivalence point. So we're at the second volume. We're at the 25.00 milliliters of sodium hydroxide. So we can get to millimoles added at that point by using the molarity, 0.100 millimoles NaOH per milliliter of solution. That gives us our 2.50 millimoles of NaOH. And then we can go ahead and use stoichiometry, that boring 1-to-1. So 2.50 millimoles of NaOH times the stoichiometric ratio, 1 millimole of CH3COO sorry. Oh, okay. I guess we're kind of, I think this seems like overkill to me, because we're basically going to prove that all of our acetic acid was used up. 2.500 millimoles of NaOH. This is for acetic acid. 1 millimole reacts with 1 millimole. 1 mole of acid reacts with 1 millimole of sodium hydroxide. So again, we've used 2.50 millimoles of acetic acid. Just to kind of prove to you we're at the equivalence point, we started with 2.50 millimoles of acetic acid. We've used 2.50 millimoles of acetic acid, so all of our acetic acid is gone. So to me, you know, and I didn't think about it till just now, but I mean, I won't, okay, I'll go ahead and say duh. I'm sorry, but that's what comes to mind. It's like, well, do you need to do that? I'm not sure. But we need to know how the millimoles of the acetate ion, and that's coming up. Okay, so the millimoles of the conjugate base of the weak acid, millimoles of CHO formed. We can use either millimoles, but we'll use the millimoles of NaOH, 2.50 millimoles of NaOH, use the stoichiometry from the balanced equation, which is a 1-to-1, so we have 1 millimole of CH3COO minus per 1 millimole of NaOH. That leaves us with units of millimoles of CH3COO minus acetate, and that's 2.50 millimoles of acetate ion. Whew. And we know what we need to do now, maybe. We need to get molarity. So we're going to take those millimoles, divide by the volume at that point. So we got, what, 25 plus 25? We got 50. So the molarity at that point is 2.50 millimoles of CH3COO minus divided by 50.0 milliliters of solution. So rounded to 3 significant figures, I got the molarity is 0.0500 molar CH3COO minus. I can't remember what my slides do next. But that is then where you have the CH3COO minus. We said it actually reacts with water to a certain extent. This is called hydrolysis. Absconds onto a hydrogen to form acetic acid again, CH3COOH plus H2, plus the hydroxide ion. Okay? So that's the chemistry at that point. Okay. So the molar, we need an ice table. So our ice table will look like, oh, sorry. Yeah. So let me go back to this equilibrium right here. So that's the thing we need to figure out at the neutralization point. So actually I'm going to write a KB expression is equal to the molar concentration of the acetic acid, CH3COOH, times the molar concentration of the hydroxide ion, divided by the molar concentration of the acetate ion, CH3COO minus. Okay, and that is equal to some number KB. The problem is that there is no, on a table, there is no KB value for the acetate ion, but there is a Ka value for acetic acid. So that's this step right here. Okay. So we know the Ka for acetic acid is 1.8 times 10 to the minus fifth. And we know that if you're talking conjugate acid-base pairs like we are for acetic acid and acetate, the product of the Ka times the Kb is equal to Kw. So we can knock out the Kb then is equal to Kw divided by Ka. So Kb for the acetate ion is 1.0 times 10 to the minus 14th divided by the Ka, which is 1.8 times 10 to the minus 5th of the acetic acid. So rounded to two significant figures, I get 5.6 times 10 to the minus 10th. Whew. So a few slides ago I said put ice table. Okay, so our ice table is going to have columns relating to CH3COO minus, relating to CH3COOH, H, and also relating to the hydroxide ion. Initial, change, and at equilibrium. So, let's see, initial would be, what did we say that molar concentration? Initial of the acetate ion, 0.0500 molar. And it's like we do these other problems like this. We're going to assume that acetic acid is 0. Well, it was kind of. And we're going to assume that hydroxide ion is 0. We're going to let x be equal to the change. So minus x here, plus x here, plus x here. At equilibrium, we have 0.0500 minus x, x, and x. Now we're going to take these equilibrium concentrations and plug them back into our Kb expression. So Kb is equal to, over here, x times x divided by 0.0500 minus x is equal to, we came up with a value for Kb right here. 5.6 times 10 to the minus 10th. All right. So, but here's the deal. And see, I kind of catch up with my notes. We are going to go ahead and apply a simplifying assumption. And we did this with other ice tables. So if we assume that the amount of acetate that hydrolyzes is insignificant, which is x, is insignificant relative to 0.0500, then this term, we'll go ahead and say if if x is significantly smaller than 0.0500, then you need to always say what your simplifying assumptions are. Then quantity 0.0500 minus x is approximately equal to 0.0500. And our KB expression becomes a lot easier. And here's my thing in red there. Remember we said, I hope this rings some bells, but we said you can do this if the molar concentration of your weak base, in this case 0.0500, if it's at least 100 times KB. And KB is 5.6 times 10 to the minus 10th times 100 is 5.6 times 10 to the minus 8th. So yeah, it's bigger. Okay. So here we go. Here's what our KB expression becomes. Much better. X squared divided by 0.0500 is equal to KB, that 5.6 times 10 to the minus 10th. Something weird about saying 10 to the minus 10th. So we can solve for x, and if we do that, we'll get x is equal to 5.29 times 10 to the minus 6th. Kind of flatten it out. You cross multiply and take the square root.
Yeah, I'm just, what, should it be 5.3? Doesn't matter.
Oh, yeah. Let's see. Because there's no, I think so. I agree.
Or is it 2 decimal places after the decimal?
Well, this isn't
That's-
applying a log function, though.
Okay.
Yeah.
Yeah. Yeah, so I think, yeah, I do think it should be 5.3. Very good. I agree. And so that's all of our x's, including this x, which is the hydroxide ion concentration. So that's where we're going with this whole thing. Okay? Which is just on the other side of basic, because 1 times 10 to the minus 7th is, on the other side, just on the basic side of being neutral, 1 times 10 to the minus 7th is neutral, right? So 1 times 10 to the minus 6th is a little basic. Okay, so we got to get a pH from that. So here goes the fun and games. All right, so let's go ahead and knock out a pOH, kind of like we did before. Apply the log function, take negative log times the molar concentration of the hydroxide ion, which I agree should be 5.3 times 10 to the minus 6th. And there, look, I give it 2 sig figs, because that is applying the log function. So don't do what I do, don't do what I do what I say. Because I really think this should be 5.3. Okay, so then we know how to get the pHs by difference. So pH is 14.00 minus the pOH, which is 5.28. And, so pH is 8.72. Dang. So that was at the equivalence point of a weak acid being titrated with a strong base.
Sweat.
I know. It's a whirlwind. And I kind of bail on the next one because the whole 30 mils, because at 30 mils, what's happened is 30 mils, this is all used up. And at 30 mils, basically, one way to look at it is you have 5.0 milliliters excess. Does that sound right? Does that make sense? Okay. So granted, we can kind of do the chemistry, and we know that actually this is actually giving us, this is making it basic. That's cool. We know that. But I would tell you the thing that's really driving the pH of this weak acid being titrated with a strong base is the excess strong base. So if you want to look back in your notes when we did HCl with NaOH, it's the same calculation at that point. Come up with the pH. All right. Well, there you go. What do you think? So we talked that weird looking S1, kind of the titration curve of your second titration yesterday. You know, this is pH, this is volume of titrant added. It kind of went like this. They were kind of fun to watch. Okay. okay, and kind of straightened out like that. Okay, that's your weak acid, strong base. Okay, so you guys, and I think this is what I kind of told you before, you guys would hopefully kind of take the straight up and down part, go halfway there, I don't know, and maybe call that your equivalence point. And we could come down here and call that your equivalence point volume, EP volume. And so your half equivalence point would be whatever this is divided by 2. So I'm just going to kind of go like that. That's your half EP volume. Okay, so here we go. And this is what you're going to need to do for your calculations. So we go up here. Okay, we see what the pH is. Pick off that pH, and that pH, if this is a weak acid being titrated with a strong base, that pH is equal to the pKa of your weak acid. And I'll show you why that is. But before I show you why that is, remember what we did in the 3 sectors of this sort of titration. The first one was making a buffer, so we used the HH equation. At the equivalence point, we used the ice chart, okay? So this region is clearly before EP. And it's before EP, you're going to use, it's a buffered solution. And if it's a buffered solution, you're going to use the HH equation. All right, there you go. With all that in mind, here we go. So at the halfway mark, does this make sense that actually the amount of acid you have left, because your weak acid is going away because you're adding a strong base, the amount of weak acid you have left is equal to the amount of conjugate base you have formed. They're equal amounts. So if they're equal amounts, you put them over each other, you divide equal amounts, and that's 1. So, of course, the log of 1 is 0. So basically, you're at a cool, interesting point in that titration where that second term in the Henderson-Hasselbalch equation, it drops out. So you are at a point where whatever the pH is at that point, the titration is equal to the pKa. Is that not cool or what? It's the little things. Okay. So this is kind of a tabulated data side by side. This was the strong acid, strong base. Okay. So I think this is where I might do an example to kind of encourage you in how do you find the equivalence volume? How do you find the volume to reach the equivalence point? So they're not always so easy. Like the ones we did on purpose were like both 0.1 molar, 25 millialiquot, 25 millialiquot, okay? Or, that's not the way it's usually going to work. So for instance, and I really, like when you find these on the test next Thursday, I really would take these, sometimes the numbers and the letters and I don't know, I would take those quantities and put them under the species they apply to. So acetic acid, we have 35.0 milliliters of 0.108 molar. Oops. And then the rest of the problem goes like, we know the molar concentration of the NaOH is 0.235 molar, question mark volume. So do I have, in the notes, do I have how to work this, or do I just kind of leave it?
You just give us the solution.
Okay. It looks like I am. So this is when in Chem 1, I encourage you to start with the thing you know most about. So go ahead and get millimoles of acetic acid, and then use stoichiometry, which is boring, 1-to-1, to get millimoles of NaOH. And then once you have millimoles of NaOH, use molarity to get volume. So it kind of looks like this. So millimoles of acetic acid in that volume and that molarity. I would put the 35.0 milliliters over 1. And then I would use, let's see, I want milliliters to cancel. I would use the non-flipped version of the molarity of the acetic acid, which is 0.108 millimoles of AA, acetic acid per milliliter. Rounded 3 significant figures, you're looking at 3.78 millimoles of acetic acid. And then to kind of switch gears, our attention to the NaOH. We use stoichiometry. And the millimoles of acetic acid, 3.78 millimoles of acetic acid, times 1 millimole of NaOH per 1 millimole of acetic acid. Of course, that gives you 3.78 again, millimoles of sodium hydroxide. Then to get to volume, we're going to use that and molarity. So I would put 3.78 millimoles NaOH over 1. And then I would use the flipped version of molarity. So the molarity of the NaOH was what, 0.235? So that would be 1 milliliter over 0.235 millimoles of NaOH. So millimoles of NaOH cancel, you're left with milliliters of NaOH, which is your equivalence point volume. Around to 3 significant figures, you're looking at 16.1 milliliters is your tipping point where you've used up all of your acetic acid. Okay. So you have an opportunity, and I don't know why necessarily, for 10 extra credit points if you do 35. Otherwise, 38, 39, 40, 41, 42, 43, 44 will we do on Monday. 45 we're going to all assign on Monday. So we'll take a quick look at those.
So these are due Monday, right?
Right. Yeah, these are due Monday. But the first one's optional. And I was like, why did I make that optional? I don't know. For this one, it threw me off because they're talking about the second ionization of phosphoric acid. But basically, if you read it a few times, you can kind of come up with, they give you volume and molarity of the potassium hydroxide, and you have to come up with the molarity at the equivalence point, that's the volume and molarities, of the phosphoric acid. And I really don't think it's too bad. You can get moles of KOH from volume and molarity. Now be careful, stoichiometry is not 1 to 1 here. It's 1 to 2. Okay? So you can get moles of KOH from volume and molarity, then you can go to moles of phosphoric acid from there, and then you can, once you have moles or millimoles, you can use volume to get to molarity. So 10 extra credit points. This one's kind of fun. If you read it a few times, basically you have sodium hydroxide and hydrochloric acid that you're going to mix together at a given volume and pH. Now, what I say in my hints is I think you're going to want to take those pHs and convert them to hydrogen ion concentrations, molarity of the hydrogen ions. Hydrogen ion over here, hydroxide ion over here. Then, it's like a neutralization, right? Basically, you count the beans and you see what you got more of when you mix those two. Do you have more H pluses or more OH minuses? Because they're going to gobble each other up when they go to fight. And so whatever you have more of, then come up with the molar concentration of that. And then get the pH from there. So it's kind of a fun one. It's a classic. They're all classics. This one, this is a strong acid, strong base, so kind of get your bearings. We covered that first today. And my hint, like I think I told you, is to go ahead and find what the equivalence point of the KOH would be. And then because you're supposed to do A, and B, I guess. In one case, you're going to drip in 10 milliliters, in the other case, you're going to drip in 15 milliliters. And I guess you wouldn't have to find out the equivalence point for this case. It would start to kind of shake out. Once you start counting your beans, you'll know if you're before or after. So that should be okay. This one is, yep, another strong acid, strong base. It's kind of similar. Again, I say, you know, maybe you don't need to find the equivalence point for these. I really think you need to, this is a weak acid, strong base. I think you should find the equivalence point there. Okay. And again, you're supposed to come up with, at 2 volumes of titrant, you're supposed to come up with what the pH is. There's a lot of problems, but what doesn't kill you will make you stronger. If some of these are similar to other ones and you're running low on time, just make sure that you can kind of do them. So A, B, and C, I kind of remind you what we talked about in class. Since this is a weak acid and a strong base, you kind of have these 3 regions. You have before the equivalence point, at the equivalence point, and after the equivalence point. So before the equivalence point, you should be thinking buffered solution. At the equivalence point, you should be thinking the conjugate, in this case, conjugate base, okay, and an ice table. And then after the equivalence point, you're like, if it's a strong base dripping in, it's just from the strong base dripping in. A weak base and strong acid. Now, we didn't do one of these, okay, but, you know, see what you think. So, in this case, I would go ahead and see how much of the titrant, HCl, you're going to need to reach the equivalence point. Your 2 volumes are 10 mils and 15 mils. That will kind of give you a sense for it. It's the same as the weak acid, strong base in that before the equivalence point, you have a buffered solution. Okay, at the equivalence point, it's being driven, in this case, by the formation of the conjugate acid. Okay, so it's very analogous. Are we done yet? Oh my gosh, we have 3 more.
2 more.
2 more? Okay. Thank you. Who's counting?
2 more.
Oh, now, this one isn't, yeah, this one is just kind of a think-through problem, and it kind of asks kind of an interesting question. Your equivalence point with a strong base, say you have a strong base in your burette, like sodium hydroxide, and in one case you're going to titrate a strong acid, in one case you're going to titrate a weak acid. They would have the same equivalence points, okay, assuming the molarities of the acids are the same, okay, but the pHs would be different, and kind of explain why that is. And one more, un más. And this is another think about question. I don't think you have to do any work for this one. But this is where, equivalence point each of the following titrations. Okay, so they give you a pair being titrated. They give you 3 different pairs, and you're supposed to say, based upon what you're titrating, what sort of acid-base titration you have, at the equivalence point, when everything's used up and all you have is product, is it going to be neutral, acidic, or basic? So I don't think you need to do any. So some of them you don't need to do any stuff. So, okay. Yay.